So we're going to look at a couple of examples of using the differential that we developed last time. So for our first example, we have f of x equals negative x squared plus 4x. And for part A, I just want us to find the differential dy, or it may just say find dy. So what we want to think about is what's highlighted in red up above, which is that dy is going to equal, so dy is equal to f prime of x dx. So some books you might even see where they say find the differential form of the derivative. So if they just say find the differential, that's really all you're doing. You're finding the derivative, but instead of writing it as dy dx equals the derivative, you're going to write it as dy equals the derivative times dx. It is important that if the derivative is more than one term, like it is here, so dy is equal to the quantity of. Those parentheses are important. So the quantity of negative 2x plus 4. So if your derivative is more than just one term, you need parentheses around them, and then that quantity times the dx. All right, part B. So for part B, let's let, and I don't remember for sure in our book or your homework if it'll say C or it might say X, one or the other, I'm not sure which. So let C equal 1 or X equal 1, and let's let delta X, so the change in X, equal 1/10. And I want us to find both delta y and the dy. Okay, so let's start with our delta y. So if you remember, the delta y is the actual change in y. So the definition of it that I had written out before, it says, something like f of c plus delta x minus f of c. So literally you're subtracting the y values. So you're going to subtract f of c, in this case is 1, plus 1/10 minus f of c, which is 1. So your delta y, your actual change in y, is simply subtracting the y values. So the ending y value, so f of 1.1, minus the initial y value, which is f of 1. So f of 1.1 would look something like negative 1.1 squared plus 4 times 1.1, and then minus f of 1 is negative 1 squared plus 4 times 1. All right, real quick off to the side here. Sorry, I have my calculator. The negative 1.1 squared plus 4 times 1.1, just typing that in real quick, that was 3.19. And then, of course, minus, this is just 3. And so we end up with 0.19. So our actual change in y is 0.19. All right, now let's go back to the dy. So remember, the dy was the negative 2x plus 4 dx. And you're going to start by subbing in kind of that nice point, that starting point, in this case that c value of 1. And your change in x, remember dx and delta x are equal. So you're going to sub in 1/10 in for the dx. So we're going to end up with, well, that's just going to be 2, and then times the 1/10. And so what we get is that the dy is equal to 2/10. All right, so one of our main conclusions was that the dy is a good approximation for the delta y when you're talking about very small changes. And this obviously is a very small change in x. We're only going by 1/10. So the last little piece here, I just want us to kind of graph and interpret what we just found, just so hopefully once again we see this sort of one more time in terms of the interpretation here. All right, so let's just get, actually here, I am going to use my little ruler here and actually get some straight lines, which I should do more often than I don't always. Okay, so there's my XY coordinate plane here. So this is my X and my, in what world, excuse me, yikes, this is my X and this is my Y axis. Okay, and let's go ahead and get a graph of our parabola here. So let's say that our parabola, this is going to be a rough sketch. Of course, you could look at your graphing calculator to get a nice good sketch here. But this is going to be just a rough sketch of our parabola here, which is f of x equals negative x squared plus 4x. All right, now we are looking at the point. We are interested in what is happening here at the point 1, 3. So, I don't know, let's just say we're not exactly drawn to scale here. Let's just say this is at x equals 1, and we'll pretend that this is all perfectly drawn. And now what I really want to have on here is some kind of a tangent line. So let me draw in a tangent line here. So let's draw in my tangent line. Okay, so what did I just find here? So I am going to have this very small change in x, which is what really kind of makes these awfully hard to draw, and why they're clearly not going to be drawn to scale, is now suppose I have this very small change in x. So let's say right here, this is my change in x is 1/10, which means I would be over at 1.1. So that's my f of c plus delta x. And so if I take 1.1, and I just kind of bring this up to my function here. So maybe it would hit the function right about here, and it hits my tangent line right about there. All right, so what did I just find here? Okay, I found out that, and again, not drawn to scale, so keep that in mind, but I found out that, and let me actually go back one more time here, and let's say I just sort of drew in a couple little extra pieces here. Okay, now what did I find? So what I found was the change in y on the tangent line. So this right here, this is my dy, that was equal to 2/10. And the delta y, so that was, I'm going to erase this just to create some space here. So my delta y, that is the change in y on the function. So this is my delta y, and that was equal to 0.19. So this was the delta y, the change in y, the actual change in y on the function. And then the dy is the change in y, I go all the way up to there, that's the change in y on the tangent line. So what we're seeing is that for these very small changes, what we're seeing is that the dy, the 2/10, is a good approximation for the delta y, which is the 19/100ths, when you're dealing with very small changes in x, like in this case 1/10. Okay. All right, let's look at one more example here. So it says differentials in application. So we're going to do one example, we're going to come back and look at some more in the next video. So it says the thickness of a manufactured shell of a sphere is 0.2 centimeters, with the inner radius of 100 centimeters. So part A, I'm going to make this part A, this first sentence here. Part A, use differentials to approximate the volume of the shell. And part B, we will then find the actual volume of the shell and compare it to the approximate volume. All right, so for part A, we are going to use differentials to approximate the volume of the shell. Okay, so first let's start off, and we need a formula for the volume of a sphere. And so the volume of a sphere is V equals 4/3 pi r cubed. So using differentials, we're taking essentially just, dy equals the derivative times dx, but in this case, the output variable is v. So dv is going to need to equal the derivative times dr. Okay, derivative is just power rule. Bring down the 3's reduce, and we just have 4 pi r squared. All right, so now we are going to use this differential to approximate the volume of this shell. So the shell is really that change in volume. So we can think about this language right here. Use differentials to approximate the volume of the shell. So when we talk about approximating the volume of the shell, our goal here, so let's just put in parentheses, kind of rephrase this, that the goal that's highlighted in yellow, I could phrase that differently and say, we'll add some specificity here. Let's approximate the change in the volume of the sphere of radius 100 as r, or let's just say with the change in r being 2/10. Okay, so this would be another way to kind of write this in slightly different language. So we're trying to approximate the volume of the shell. So that means we're trying to approximate the change in volume, specifically the change in volume of the sphere, right? That's what I'm talking about. So it's the change in volume of the sphere. So the change in the volume of the sphere will be then just the volume of the shell. So if I can approximate the change in volume of the sphere of radius 100 as we go from, or I guess I can delete that word as, with the change in radius of 2/10 of a centimeter. Okay, so let's go ahead and do that. So we now have our dv. We've kind of rephrased this a little bit. So let's get back to work on the dv part here. So our dv is going to be 4 pi. Our r in this case is the 100 squared. And the change in r, the delta r is the same thing as the dr. And in this case, this is our 2/10. So if we multiply out the 100 times the 4 and then times the 2/10, that all comes out to be 100 squared, I should say. That gives us 8,000, and then we still have our pi. So this would be in terms of cubic centimeters because it is a volume. So this would be our approximation using differentials for the volume of just that shell of that sphere, so just this outer shell. So we use the differential to approximate the change in volume if I started at a radius of 100 and then I had this change in radius. I went out with my radius of positive 2/10. Okay, well now let's actually then, so we're still kind of in this similar kind of as the last example where we find both the kind of the approximation with the differential, and then the actual change, and then just kind of observe that they are in fact close if we're dealing with these small changes. All right, so then the actual change in volume, so my actual change in V, remember, so that's going to be just subbing into V, and it would be subbing in the V of 100 plus the 2/10 minus the V of 100. So it's just subtracting what the actual volume would be with a radius of 100.2, and then subtracting from that the volume if the radius was 100. Okay, so change in V is going to be 4/3. This is the formula for volume, so actual volume here, 4/3 pi, and then 100.2, that's our R cubed, minus 4/3 pi, and then the 100 cubed. And again, you could factor out maybe like a 4/3 pi on that, but I've already taken the liberty, I've subbed this into my calculator already. So this ends up being 8,016.01 pi, and this would be in cubic centimeters. Okay, so this would be our actual change in volume. Okay, so once again, as we kind of think about those two, so what we had here, so this was our actual change in V, and then of course up above you had your dV there. So what we're observing is that the dV was a good approximation for the actual change in V. So when we come back next time, we're going to kind of add to this idea a little bit. We're going to look at some more applications. In particular, we're going to look at applications involving error.